Welcome in. Grab your notebooks, pencil, pen, whatever you want to write with, it's fine. As long as you can follow along and give this very tough problem from related rates an attempt, okay? This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 1996 AP Calculus BC exam. We have this problem with an oil storage tank defined by this equation revolved around the y-axis. That is some useful information. That means we're probably going to be doing some integrals dy. X and y are measured in feet, and it goes from x is 0 to x equals 5. So the widest is at the top of the oil storage tank. And oil, which weighs 50 pounds per cubic foot, okay, I'm not sure what that has to do with it, but maybe we'll see it later, is flowed into an initially empty tank at a constant rate of 8 cubic feet per minute. It's another interesting, useful bit of information. So it's filling it up, and they tell us how fast it's filling it up. dV dt, the volume, is equal to 8. All right. When the depth of oil reaches 6 feet, the flow stops. Okay, so we're just filling it up to about 6 feet of height. That's the highest it's going to go. But you can see that we're kind of filling up these discs, right? These disc shapes, all the way up from starting from the bottom and making our way up. And the discs are getting wider because as we go up the tank, it gets a little bit wider according to this quartic graph. Okay, let H be the depth in feet of oil in the tank. How fast was the depth of the oil increasing when H equals 4? So they want to know dH dt. Gotta try to find dH dt. How fast is this oil increasing? Well, let's take a look. We have that the height of the oil depends on how much oil has been put into it. Is that right? So dV, or rather dH dt, is going to require us to do the derivative of the volume. And dV dt is just the derivative of the volume. So we're going to need an expression for the volume, right? The volume is simply the total amount of oil that's in there. So we're going to basically take an integral from height 0 to h of these disks. Each one of these disks, and we're going to be integrating with respect to y. So each one of these disks has a radius equal to x, but we have the equation y equals f of x. We need to switch this around a little bit. And the area of each one of these disks is going to be pi times x squared. So if we can add up these sort of slices of oil, so to speak, from 0 to 6, then we can determine the overall area. So let's find out what x is if we take this equation and kind of solve for it. We're going to end up with 625 over 9 y equals x to the 4th. And if you just take a square root of that, you get 25 over 3 square root of y. That's equal to our x squared. That's good enough. We could just plug that in. So the area of each one of these disks is 25 pi over 3 times the square root of y. And therefore, that's going to be our volume. Bring the pi out front. 25 over 3 square root of y dy, but we want dv dt. So we're going to have to use the fundamental theorem of calculus here. All right, so when we use this fundamental theorem of calculus, a lot of times what I'll say is we're going to do doing like ddt, for example, or sorry, ddx of an integral from 0 to x of f of t dt. What I'll usually say is we should write this as the derivative of, don't jump straight to the derivative of capital F of the top limit minus capital F of the bottom limit, where capital F is just the antiderivative, right? Which means that we have to consider the chain rule when we take the derivative next. So we have to consider the chain rule. It's not just going to be 25 pi over 3 square root of h. It's going to be 25 pi over 3 square root of h dh dt. And this is what's going to allow us to solve for the thing that we're supposed to solve for in the first place. This is the first signs of seeing dh dt. Oh, sorry. And we've already taken the derivative there. Okay. Got it? So when we take the derivative, it's kind of like we're doing the derivative of 25 pi over 3. Let me just call it this for no particular reason. I'm going to call it capital Y of h minus capital Y of 0. And when we take that derivative, we get, again, 25, not 2 pi. 25 pi over 3. Let's just call this the function at h, so square root of h, minus square root of 0 just goes away. But we have to multiply by the derivative of h because of the chain rule. Right? This is a related rates problem. So we have to multiply by that implicit derivative. And again, we know this is equal to 8. Now, they're telling us a specific moment here. They're saying when h is equal to 4, we have to also use this condition. So when h equals 4, then we're going to end up with 8 times 3 equals 25 pi times square root of 4 dh dt. So therefore, we divide by 2, we divide by 25 pi actually as well. This could just be 12 over 25 pi is your dh dt. And let's put that in the right units. I don't know if they said to indicate units, but you should always check. Indicate units of measure. I forgot to underline that in red. Indicate units of measure. So this is feet, right? Per, what are we talking? Per minute? Yeah, because the flow of the oil is in 8 cubic feet per minute. So this is going to be feet per minute. Oh, and I mean, if you want to get an exact value for that, go for it, multiply it out, do you? If you need a calculator, I think you do need a calculator because the next problem is saying find to the nearest foot-pound. That's very specific. The amount of work. Interesting. Work is an integral of f dx. I don't know if you knew that from physics, but that's true. What's the amount of work required to empty the tank by pumping all of the oil back to the top of the tank? Oh boy. Okay, so now we have this thing full of oil, and we want to pump like most of it out. So keep in mind, these discs that I've been drawing, these cross-sectional discs, they each have a different amount of distance to go in order to get out of the tank, like up and out of the tank, right? The whole thing is 9 feet tall. But depending on what the current oil level is, that determines how far it needs to go. So the dx, or rather in this case, it's like the dy. It's going to be f dy. The dy, this little tiny thickness here, this is going to be 9 minus y. Right? So whatever the height is, 9 minus that's how far it is from the top, basically. Pretty straightforward. So if the height is 5, and the whole thing is 9 tall, then that means it has 9 minus 5, or 4 feet to go to get out. So this is going to be from 0 to 6, 9 minus y. And what's the force? The force is like, the weight here. 50 pounds per cubic foot. So 50 pounds per cubic foot. Remember, what is the size of these discs? These horizontal discs, have an r value, which is equal to x. And again, the formula is pi r squared, which means pi x squared. And since we solved for x squared, this is pi times, 25 over 3 square root of y. Okay, and I mean, they technically have a little thickness, very, very tiny thickness of dy. So that's the volume. So v equals pi times 25 over 3 square root of y dy. So if we put all of that together, here's the distance that it has to travel. Here's the force, that's the volume. So the force is 50. Now we're getting somewhere. Work is equal to, it's 50 times that, times 25 pi over 3. I might as well bring all the constants out front because this integral is going to look kind of messy. The height goes from 0 to 6 because we're talking about where the oil level is going to be filled up. It's going to be, technically we're draining it from 6 to 0. But no, actually, if you think about it, the way that some of these pumps work, they're at the bottom, right? And they're pumping it up. So it starts with everything that's at the bottom, which seems not so efficient, but there's less weight pushing down as you go. So you're using gravity to help you pump it up, right? The gravity of the oil that's on top helps make it easier to push this stuff through the pump. Okay, anyways, so times the square root of y, basically. Yeah, just square root of y times 9 minus y dy. And you guys can plug that into a calculator if you want. 50 times 25 pi, well, that's pretty easy to do. That's just going to be 1250 pi over 3. And then integral from 0 to 6 of 9 y to the 1/2 minus y to the 3/2 dy. Or you can plug it into your calculator, dx, and you'll get the answer. I'm not sure what it is. Especially since you need to round it to the nearest, what is it, foot-pound? To the nearest foot-pound, so to the nearest whole number, basically. No idea what that is, probably like 60,000 or something. It's going to be very, very high. It's a pretty big tank. All right, so that covers our exploration of this pretty tough related rates problem. It's related rates, but with integrals, and this work concept, which if you're in physics is a little more familiar. If you're not in physics, a little less familiar. All right, that'll do it for me. Enough blabbing. See you guys next time in the void.